Got it? All right. I will begin with a word of prayer. So, dear Heavenly Father, we thank you for the break just completed. Just pray that you help us to wake up this morning and learn some more math. In your name I pray, Lord Jesus. Amen. All right, so I'm going to get right into it. It's a root test. Yep. So this is theorem. So 12.4 is root and ratio tests. All right, so here it is. Theorem. Let a sub k be a series with non-negative terms. And suppose the kth root of a to the k, a sub k, goes to rho as k goes to infinity. Right? Then, three cases. Well, really two cases. The third case, if you read a different book, might not be there. But it's nice for pedagogical reasons that it's there. If rho is less than 1, then the series converges. If the quantity rho is greater than 1, the series diverges. And then case 3, if rho is equal to 1, this test is good for nothing. That's not what it says in the book, but that's what it means. Okay. In other words, if rho is equal to 1, the test doesn't really apply. It doesn't apply conclusively. It's inconclusive in that case. So, as we go over these various tests, it's important I take a few minutes to prove each one of them so that it's not just some sort of black box magic we're using. It's not hard to prove this. Let's see how it goes. It's very hard to prove with this marker, actually. Fine. Dead to me. Oh, slight overshot. That was my last blue marker. Oh well, proof. So case 1, let's assume that the kth root of a to the k goes to rho, where rho is less than 1. Okay? So if that's the case, that means you can choose some mu in 0 to 1 such that what? Well, 0 is less than mu is less than rho is less than 1. Certainly that's true, right? If your limit is rho and rho is 0.7, you could pick something less than 0.7, right? And the point of that is that if that's the case, then there's got to be some k, right? There's got to be some k that if you're past that k, for sufficiently large k, you're going to have what? A sub k to the 1 over k is less than maybe less than, wait a minute, a second here. Yeah, less than mu. Oh, I'm sorry, I did this wrong. That's not what I want. I could do that, but that's not what I want. That's not what I want. Actually, I want the other way, okay? I mean, I can certainly do either, but this one is more helpful. Okay. So I mean, if the kth root is getting really close to rho as k goes to infinity, right? It must be the case that eventually the values of the kth root of a to the k are settling close to rho, right? Which means beyond some point, all the values have to be less than mu. Does that make sense? Do you see what I'm saying? If this is a picture, here's, rho. And we're looking at the kth root of a to the k as the sequence here. Then that's rho. And where's mu in this picture? Mu would be like up here, right? And here's 1 up here. So if you go far enough out, all of the kth roots of a to the k, a sub k must be less than mu, right? So for k sufficiently large. Does that make sense? Why you can do that? Here, the k sufficiently large would be what? Basically here. In my picture. So then what? Hence, well, a sub k is less than mu to the k, right? But that's pretty much all we need. Notice the sum. We'll look at k equals 0 to infinity, but you could start it at somewhere else if you wanted to. It would just clutter things up a bit, but certainly the sum k equals 0 to infinity of mu to the k. Well, we already know that. What's that? That's a geometric series, right? With ratio mu. So that converges, in fact, to 1 over 1 minus mu, right? So it hence converges as 0 is less than mu is less than 1, right? And by the basic comparison test, fine, I'll write it out. Some other books will call the basic comparison test the so-called direct comparison test because it's a direct comparison test, right? Any questions? Right, so we have a series with terms which are larger than a sub k converging. Consequently, a sub k must also converge since it's bounded below by 0, right? Okay, now that's case 1, right? How do we do case 2? I'll try to go through this one a little bit faster. If we have a sub k to the 1 over k goes to rho, and rho is greater than 1, then there exists mu such that 1 is less than mu is less than rho. So you can go the other way. You can still find something closer to 1. And such that a sub k to the 1 over k is what? Is greater than mu for k sufficiently large. Sometimes I like to write this for k much, much greater than 1. This is a convenient shorthand for saying k sufficiently large. You guys like notation like that, right? This means for k sufficiently large. Now, so then what do you have? A sub k is greater than mu to the k, right? And mu sub k goes to infinity as k goes to infinity, right? Since mu is greater than 1, thus a sub k also goes to infinity, which of course we have a sub k is not going to 0, right? Thus the series diverges by kth term test, right? You could run through this, the argument of 1, just pretty much the same, and you'd also get to it. You get to the series being larger than a divergent geometric series if you followed the proof of 1 all the way through the same way. But really the point is it diverges by the kth term test. How about case 3? To show it's inconclusive, it suffices to give you 2 examples, one which converges, one which diverges. And the standard example to look at would be like P series. So you could look at P equals 1 series. Diverges, right? What's the P equals 1 series? Sum k equals 1 to infinity of 1 over k. This diverges, all right? But a sub k to the 1 over k is what? That's equal to 1 over k to the 1 over k, which is equal to 1 over k to the 1 over k, which we proved back in section 11.4 is what? You've got, what do you got here? This is going to infinity, that's going to 0, and we proved that k to the 1 over k in fact tends to what? As k goes to infinity. We proved it goes to 1 back in section 11.4. So here we have 1 is equal to rho. We're in case 3. Here's an example where we have rho equals to 1, it diverges. What's an easy case of a convergent thing? How about p equals to 2, right? P equals to 2 is a convergent series. P equals to 2 series converges. And the p equals 2 series is in particular the sum of 1 over k squared. K equals 1 to infinity, all right? So in this case, you have a sub k to the 1 over k is equal to what? 1 over k squared to the 1 over k, which is, by the way, the same as 1 over k to the 1 over k quantity squared, which goes to 1 over 1 squared, which is, of course, 1, which is equal to rho. So there you have it. If the root, the kth root tends to 1, well, then you don't know. It could be convergent, it could be divergent. You just can't say. Let me show you an example. Let me show you an example or two. All right. I like this example in the text. It's a nice example. And if actually, once you understand this example, it's pretty easy to see that you could, let's say k equals 1. Oh, that's probably, can you guys give me reasons I shouldn't put k equals to 1 here? Let's say k equals 2 to infinity. Natural log of 1 is 0, right? K equals 1 would be, it would be not a good formula. Okay, so here what do we have? We have a sub k is equal to 1 over the natural log of k to the kth power, right? So therefore, a sub k to the 1 over k is just equal to 1 over the natural log of k. Right, because the kth root of the kth power is just what you have again as k goes to infinity there. And so what does this do? Well, this does what? This goes to 0, right, as k goes to infinity. Therefore, by root test, we have that the sum 1 over ln of k to the k power converges. I like this example because it gives me ideas. I mean, if you think about this, can you think about like tons of other examples? You could come up with a lot like this. Like, think about this. If I had basically anything of the form, some whatever appropriate range, 1 over, like b to the b sub k to the k, right? This is going to converge if what? What condition do you need for that to converge? You need, well, like b sub k to be positive, right? I don't know what to do with negative terms just yet. That's section 12.5. But if I have b sub k is positive, and what? If I have b sub k does what? Goes to what? Fill in the blank. What made the example above work, like the b sub k was natural log k, right? The fact that the natural log went to infinity is what made that work, right? If I could just replace natural log with anything else that goes to infinity, same pattern, same argument, root test will give me converges, right? It's like if you have a homework that's like 1 over k to the k, root test, right? Anything that's going to infinity to the k power root test will dispatch with ease, provided that, of course, we're looking at positive terms. Another example. Let's see here. Some, let's say 3 to the k over k cubed. All right, we'll say k equals 1 to infinity. So here, if you look at a sub k to the 1 over k, what do we have? We have 3 to the k divided by k cubed to the 1 over k, which is what? 3 to the k over 3 over k, right? So, I mean, you guys probably have picked up on this, but we're using these rules all over the place, right? ab to the s power is a to the s, b to the s. And a over b to the s power is a to the s over b to the s, right? Like that's what I did here. This is, and then of course also a to the s to the t is a to the st. We're always using these laws of exponents here, right? Like this is 3 to the k times 1 over k or k over k. Okay, so anyway, rewriting this, we got what? 3 to the 1, which is 3. And downstairs, I've got what? I would rewrite this as k to the 1 over k cubed. Now, the reason I'll do that is because I have just mentioned over here that we know from section 11.4 that k to the 1 over k goes to 1 as k goes to infinity, right? So if I can see k to the 1 over k, I already know what that does. It goes to 1, referring to section 11.4 and a known result. So this goes to 3 over 1 cubed, also known as 3. So this is the root, the row. So therefore, the sum k equals 1 to infinity of 3 to the k over k cubed diverges by root test with rho equals to 3, which of course is greater than 1. Let me show you a problem I might have assigned. I thought, I'll just pick a problem out of the end of the section, work it as an extra example, see how it goes, right? So, oh, fine, just mind my own business. I tried this out. Sum of the natural log of k divided by k to the 5/4. And I suppose it's k equals 1 to infinity. All right. This is actually number 32 of section 11.4 in my book. Okay. So okay. All right, well, I'm going to try the root test, right? Was the question? No? Try the root test. What do you got? You have a sub k to the 1 over k is what? Natural log of k divided by k to the 5/4 to the 1 over k, which is what? Natural log of k to the 1 over k over what? K to the what? Five over 4k. All right. So in other words, that's the natural log of k to the 1 over k power. And let's see here, down here I have k to the 1 over k to the what? To the 5/4 power. So the denominator there I know goes to 1 to the 5/4, which is 1, right? Now the numerator, I'm not sure about the numerator. That's indeterminate type. How do we figure that one out? I got natural log of k to the 1 over k. What's that do? That's infinity to the 0 power. That's indeterminate type, right? So I do what? I do exponential of the natural log of this thing. And I rewrite it. Okay, so that's exponential of 1 over k times the natural log of k, right? In other words, it's the exponential of the natural log of k over k, right? Note, the natural log of k over k goes to 1 over k divided by 1 by L'Hopital's rule on type infinity over infinity, right? And that goes to 0. Hence, this is the exponential of 0, which is 1. Well, I should say it's going to that. Right. Yes, sir. I'm sorry? Which second step? Oh. Oh, man. Oh. Hey. Well, thank you. Maybe this is more interesting than I thought it was. Because the moral of my story was going to be here that the root test doesn't apply. You have given me new faith in this problem. I hope I'm wrong. Thank you. So you're like, it should have been that, right? Yeah. Yeah, duh. Oh, not that either. That's not right either. Oh. Goodness gracious. Well, this break has done well for you guys. I'm very happy. All right, so this is the natural log. I'm actually very happy when I'm wrong, guys. I want to be wrong. If I could be wrong and you guys could be right, that'd be wonderful. I mean, I'd like that. That'd be good. I'd like more of that. Let's see here. I mean, I would also be happy with us both being right. I mean, I would also be content with that. Let's see, natural log of 1 over k temp. Do we agree with this? Properties of log, bring that down. But then this is what? That's the natural log of 1 over k plus the natural log of the natural log of k, right? No. Okay, that's enough no's. And this is why parentheses are your friend, right? They keep you from doing this stupid thing. My interpretation here would be what? That this is natural log of this, right? But is that what that means? No. We're looking at the natural log of k to the 1 over k power. That's where the parentheses are. So this is not, man. I hope this was helpful. All right, so I get 1 over k, natural log of the natural log of k. I knew something was wrong with what I just wrote as soon as I wrote it. I just had to pause and reflect on it. Okay, now do we all agree? Does that make sense now? Okay, so I can rewrite that. I can understand that. That's really the exponential of what? Well, let's go off to the side here. Note that the natural log of k over k, right, is by L'Hopital's rule on type infinity over infinity. 1 over the natural log of k times 1 over k divided by 1. Now, this goes to infinity, that goes to infinity, that's 1. So this is still going to, it's still going to, well, I have mixed emotions about all this. We still get, this is going to exponential of 0, which is 1, right? My hopes have been dashed. I mean, it's fine. So this gave us that, right? Now, and so if we look at this result here, what do we have? This goes to what? 1 over 1 to the 5/4, which is otherwise known as 1, right? Yay! So what have we shown? We have now verified that the root test is worthless to us here. Now this section is on the root test and the ratio test. This is a problem from section 11.4. If we knew what the ratio test is, we could try that as well, okay? Let's talk about what the ratio test is, okay? And then I'll come back to this example. Spoiler alert, the ratio test is also not going to work. You're like, what? What evil is this that they would put a problem in this section where neither of the tests central to the section work on it? Well, that's part of the game we're playing, right? You have to come to an understanding that you have a lot of different tools to use, and sometimes It may not be the one that you're immediately thinking of. All right, where was I? Where was I? So the ratio test, all right, so what is the ratio test? .4.2, so-called ratio test. Let sum over a sub k be series with positive terms, so a sub k greater than 0, all right? And suppose the ratio a sub k plus 1 over a sub k tends to lambda. Then 3 cases. Case 1, case 2, case 3. Case 1, lambda less than 1, the series converges. If lambda is greater than 1, the series diverges. If lambda is equal to 1, the test is good for nothing, except to tell you that you need to go consult other professional advice. Let's see here. It's inconclusive, right? Let's look at the proof of this. Let's suppose a sub k is greater than 0, and the quotient a sub k plus 1 over a sub k tends to lambda for some lambda less than 1. Okay? And okay, so we're going to kind of play the same game again. We can choose what? We can choose mu such that what? 0 is less than lambda is less than mu is less than 1. So you can pick something between lambda and 1 again, right? And since the quotient a sub k plus 1 over a sub k is tending to lambda, by essentially the same picture as I was showing you over here, we can again choose k sufficiently large such that what? Let's say for k greater than or equal to k naught, for some k naught in the natural numbers, we have what? We have a sub k plus 1 over a sub k is greater than what? Less than what, rather? Sorry, I'm an idiot. Less than mu, right? Because the quotient settling in on lambda, right? The value mu is above lambda, so it has to be getting away from that as you go far out where it's converging to the value lambda, right? So then what? Well, you just start thinking about case by case for just a second here. We'll figure something out. So if you look at this, this means what? A sub k naught plus 1 is less than mu times a sub k naught, right? I mean, you can, this implies what? A sub k plus 1 is less than mu times a sub k for k greater than or equal to k naught, right? So for k equals to k naught, you get this. How about a sub k naught plus 2? What do you get? it's recursive, right? So I can feed the first inequality into the second one. What do I get? I get this is less than mu squared times a sub k naught, right? Because I get mu times mu. So just keep doing this, right? Well, if we have a to the k naught plus j, that's less than, right, mu to the jth power times a sub k naught. See, this is j equals 1, this is j equals 2, and you just keep doing this. You'll get that. But what does this tell us? So we see what we want to do is setting k equals to k naught plus j. What's that make j equals to if I make this substitution? What would j be here? J, solve for j, right? J is equal to what? K minus k naught? Yeah? What's the question? My handwriting? These are both j's, all right. So this gives me what? A sub k is less than mu to the k minus k naught times a sub k. But we can rewrite this, a sub k naught, right? This is what? This is equal to a sub k naught divided by mu to the k naught times mu to the k. Now, notice here that this thing that I put in parentheses, this is just some number, right? There's no dependence on k to this number, right? And this thing I just wrote is true for what? It's true for k what? Still for k greater than or equal to k naught, right? But that's all we need when we're thinking about the series, right? To apply the basic comparison test, all I need is an inequality to be true for k much, much larger, for k sufficiently large. If I have that, then I can apply the comparison test, and so there it is. I mean, this is going to give me thus the sum over a sub k converges by basic comparison test as, the sum of a sub k naught over mu to the k naught of mu sub k is equal to a to the k naught divided by mu to the k naught power times the sum over mu sub k, mu to the k rather, which converges by geometric series. So here r is equal to mu, which is less than 1, right? It's kind of funny, right? Both ratio test and the root test, what are they really built over? This geometric series, right? It's everywhere. So I mean, geometric series is just so important logically to everything we do here. Okay, so now we have this, and by the way, the proof of 2, again, the fact that it diverges is easy to prove. Use the kth term test. You can easily show that if you have that, you can show that a sub k, in fact, does not go to 0, hence it diverges by the kth term test. To prove inconclusive case 3, again, you can look at the p equals 1 and p equals 2 series. Both of those have ratios which work out to 1, and yet the p equals 1 series diverges, whereas the p equals 2 series converges. So the inconclusive case. And then, and here, you have, natural log of, if you look at this example that I was playing with over here, if we look at a sub k plus 1 over a sub k, that will give us the natural log of k plus 1 divided by k plus 1 to the 5/4 times k to the 5/4 divided by the natural log of k, multiplying by the reciprocal. And, well, this is equal to k divided by k plus 1 to the 5/4 times the natural log of k plus 1 over the natural log of k. And in fact, you can show that this goes to 1 and that goes to 1, so the whole thing goes to 1. So the ratio test is also worthless for this problem. Okay. I'll come back to that problem in a minute. Let me show you a more positive example of the ratio test before I do, though. Let's see here. Actually, I'm going to be a little bit greedy here. I'm going to give you an example which is kind of a double example, since we're a little short on time here. So here's the example. Sum, say k equals 1 to infinity of k to the k over k factorial. K factorial. I don't want to take the kth root of k factorial. I just don't. I mean, I don't know. So this seems like a good job. Generally speaking, factorial to me makes me think I should try ratio test, because the beautiful thing about ratio test is it does nice things to factorials. When you take the quotient, right, a sub k plus 1 over a sub k, what's that? That's k plus 1 to the k plus 1 power divided by k plus 1 factorial, all right, times what? 1 over a sub k. 1 over a sub k, though, you see, is k factorial times k to the over k to the k. I'm using a little algebra trick here. Do you see what I'm doing? Do you guys understand what I'm doing? I could write k plus 1 to the k plus 1 over k plus 1 factorial divided by k factorial divided by k to the k. But why write that when it doesn't really get you anything? Why not just write it in a more algebraically useful way as a product of two fractions, right? What have I done? Ah! Yeah, don't do it this way at all. Thank you. So with that, then there's some very central identities here. So first of all, the first thing upstairs, I have k plus 1 times k plus 1 to the k, right? Divided by k plus 1 factorial, well, that's k plus 1 times k factorial, right? That's the go-to identity for the factorial. You can basically recursively define it by that. And well, this other one, still k factorial over k to the k. But there's some just wonderful cancellations that happen right here, right? So k factorials cancel. K plus 1 and k plus 1 cancels. And you can re-express this, right, as k plus 1 over k to the kth power. Yeah, that's all that's left, right? And we can rewrite that. That's actually 1 plus 1 over k to the kth power. Well, hey, that's the exponential function evaluated at x equals to 1. We've proved before that this goes to the value e as k goes to infinity. Okay? Section 11.4. Thus, the sum k to the k over k factorial, k equals 1 to infinity, diverges by kth term test. Good grief. By doofus. Ratio test. All right. So likewise, the sum over k factorial divided by k to the k equals 1 to infinity, converges as a to the k plus 1 over a to the k goes to 1 over e by a similar calculation, right? And again, using the ratio test. So if we have division by k to the k, it forces convergence. Basically, k to the k beats k factorial, right? So how do you work that problem over there, man? I'm going to let you guys stew on that. I'm going to add another day to your homework because I wanted to have time for homework questions today. I'm just not where I need to be yet. So I'll collect the homework, which I said I threatened to make due tomorrow. I hope you're mostly done with it. But I'll try to leave some time at the end of class tomorrow to talk about homework. I still have to cover 11.5, but hopefully we can cover 11.5 and still have 20 minutes or so for homework, something like that. Oh, I suppose I should give you back your test, huh? Let's see here. Let me find the start of you guys in here. Jordan, Charles. Is Jake McMasters in here? Oh yeah, you can turn that off.